Next, let's hear from Sri Lakshmi Murthy, Senior Software Engineer from MathWorks Private Limited, about how simulation and modeling can help predict and shape the future.
Check. Am I audible? Yeah. Hi, folks. Good evening. I am Sri Lakshmi Murthy. I work as a senior software engineer in MathWorks, Bangalore office, and I work for some of the features for Simulink, which is one of our flagship product. And the topic that I'm going to discuss today is predict the future using the power of simulation and modeling. Before I start my session, I just want to tell that all the views that I'm expressing in this session are my views and do not represent that of my company. With that, let's begin. So the agenda for today is to understand the need for predictive maintenance, and then we'll walk through the predictive maintenance workflow, and then try and understand what is remaining useful life, which is one of the benefits of adopting predictive maintenance. And then we will understand some of the common ways to estimate the remaining useful life, in short, RUL. Every day, we rely on a number of machines, and eventually, these machines are going to fail if they are not maintained properly. So organizations are always on the lookout to find maintenance strategies in such a way that they do not spend a lot of money maintaining them, but at the same time, they also have to make sure they do not go bad when they are functioning. So what are the different maintenance strategies that organizations can follow? Well, the first one is reactive maintenance. Well, what really happens in reactive is nothing. It's a do-nothing strategy, wherein you wait for the equipment or the machine to go bad, and once it has gone bad, you just go and replace it. This is kind of a good strategy to follow if you are dealing with some simple equipment like a light bulb. But what if we are dealing with a complex equipment like an engine? Well, you don't want your engine to break down when you're in mid-air, right? So organizations try to follow some different strategy in this case, which is scheduled maintenance, wherein at regular intervals they try to service the engine. The problem with scheduled maintenance is that even though they have scheduled a maintenance and then the engine is serviced, it may so happen that they may not be able to find the problem, and eventually the engine will still break down. And also the problem with this is that when they have scheduled for maintenance, it does involve a lot of money. So they need some sort of a balance in order to make sure the maintenance is scheduled just before the engine can break down. So that is what predictive maintenance does. So one of the benefits of adopting predictive maintenance is that it can also pinpoint what is the problem with my machine, and also for how long can I use this machine from the point, from the current condition to the point it can fail. So just to give you a more real world example and make you understand the need for predictive maintenance, let's consider this real world example. Anyone here, can anyone tell me why this system is used, or what is the usage of the system? Can anyone in the audience can give it a shot? No one? Okay. So this is a system that we use in order to extract oil from the refineries. This is a Baker Hughes oil extraction system. The cost of this system is about $1 million, and at the heart of the system, we have a triplex pump. So this triplex pump has a lot of moving parts, and with a lot of moving parts, that means it has to be maintained at regular intervals. And a lot of times, what goes wrong in this system is that one or two of the valves that are present in the pump can go bad, and the cost of repairing it could be around $200. But what's the big deal, right? You can tell me they can just schedule maintenance at regular intervals, go ahead and repair all the valves. Well, it's not that simple. In order to understand why, let's see where it is actually used. This is an oil well site wherein we are going to use this extraction system. And what happens here is we notice that at least 20 of those systems are working in tandem. And each of the system is subjected to different operating condition. And as a result, it's almost impossible to know when the valve is going to break down. So what to do? What they generally do is they have a very, very expensive safety backup net here. They have 5 of those backup systems that are present on the site, and then these serve as a backup whenever one of the system fails. Well, this is a very expensive safety net. So as an alternative, we could adopt predictive maintenance in this situation, where in case of predictive maintenance, what happens is we have the triplex pump. We try to collect the data from the sensors that are placed on the pump and then pass it to a predictive maintenance algorithm. And this algorithm, in turn, will be able to tell when the pump is going to fail. So based on when the pump is going to fail, we can schedule maintenance and then get it repaired. So this is what a predictive maintenance algorithm does at a higher level. Now, let's see what all an algorithm can do for you. Given the data that is given, it can tell if my machine is operating normally. That's called anomaly detection. Or it can also tell why is my machine behaving abnormally, which is called condition monitoring. And thirdly, it can tell us how much longer can I operate my machine, which is called the remaining useful life. So one can make these three decisions using the data that is available. Now that we have understood the need for predictive maintenance and we have also understood what a predictive maintenance algorithm can do, let's see how it actually does that. So the first step that's involved in creating a maintenance algorithm is acquiring data. So we acquire a lot of this data, either from the pump itself or we generate some of this data. And then the second step is, now that we have a large set of data, it's quite normal that some of the data could be faulty or some could be duplicate. So we need to do some amount of cleanup, which is done in the pre-processing stage. Then we identify the condition indicators, which is nothing but extracting the features. Then we train the model using these extracted features, and finally deploy and integrate the model onto an edge device, which is connected to the pump. So in the interest of time, in this talk, we are going to focus mostly on acquiring the data part of it and training the model and ignore the other steps. So let's begin with acquiring data. Like I told you initially, this triplex pump has a lot of sensors which is used in order to get the temperature, flow, pressure, and such details and other parameters. So we collect the data using these sensors, but in order to develop a very robust a good algorithm, it is necessary that we have a large amount of data, and large amount of data which includes both healthy as well as faulty scenarios. So what do we do? How do we really get failure data? Because a lot of time from the pump, what we get is mostly healthy data. So what we do? We use simulation. So what one could do is, using the specifications of the pump that is already available, we could build a model using one of the softwares that are available in the market, or one could also use Simulink, which is one of our flagship product. And then we can fine-tune the model using the sensor data that's available, then inject failures in order to incorporate the failure modes. This will result in running a lot of simulations that in turn will generate a lot of failure data. So now what we have is the real sensor data, and also from the simulation we have a lot of synthetic data that's available. Both of them can be given as an input to the next step, which is the pre-processing, wherein the data will be cleaned up, condition indicators will be figured out, and after that we use these condition indicators in order to train a model. So we can train a model in order to detect the anomalies in our system. By anomalies, I can tell you like whether the system is behaving properly or not. So one can do that, or we can train a different type of model in order to find out what is the fault in my machine. So that is identifying the fault type. And the third thing that one can use this information is to detect the remaining useful life of the system. And for the remainder of this talk, I'm going to mostly focus on the remaining useful life, which is one of the benefits of adopting predictive maintenance. So what exactly is remaining useful life? Well, what you see here is a machine deterioration profile. The blue dot that you see is the current condition, and then the red dot that you see is the failure condition. The time it takes for the machine to go from the current condition to failure condition is the remaining useful life. And there are several RUL estimator models that are available based on the amount of data that you have. So the three important models that I'm considering in this case is the survival model, degradation model, and similarity model. So what exactly happens in the survival model? In the survival model, the data that you have is only failure data from similar machines across. So in this case, if the yellow line that you see is the pump that is in operation, it is telling that this pump is in operation for about 20 days. Now, all the red dots that you see are the pump failures. So it is giving me two details. It is telling me for how many of these pumps failed after how many days, and also it is telling me um, by using this data, what I can do is I can do a probability distribution function, and using the median, I can get the remaining useful life. So this is about survival model, wherein I can deduce the RUL by just using the failure data from similar machines. Now let's consider another type of model, which is degradation model. In case of degradation model, I don't have any failure data at my disposal, but what I do have is only healthy data, and along with the healthy data, I do have some knowledge about the safety threshold value. So in this case, what would happen is I have a safety threshold value. I know the pump that is in operation. So by using the past values of the condition indicator, I can determine, or I can fit a degradation model and determine when this condition indicator is going to reach the safety threshold. Based on that, I can actually find out what is the remaining useful life. And the third type of model that I'm going to talk about is similarity model. In this case, I have like the whole set of data available to me, which is healthy data, faulty data, and also the safety threshold value. So with all these three information, I should be able to do a good probability distribution model and then actually find out a remaining useful life with a very high degree of accuracy. So just to recap, in this, what we discussed so far is based on the amount of data that's available. In survival model, just with the failure data, you can determine the RUL. With degradation, you have the healthy data and the safety threshold value. And with similarity model, you have the full set of data. So in conclusion, I would like to say that today we discussed what is the need for predictive maintenance in determining the health of our system. We understood the predictive maintenance workflow. We explored the common estimation models to predict RUL of a system. And also finally, we understood how to choose the appropriate RUL model. Thank you.
Thank you for such an inspiring talk, Sri Lakshmi. I'd now like to invite the session chair to present a token of appreciation to Sri Lakshmi.